Hi viewers, welcome to my class on mechanics of materials. In today's class, we will continue to work out numerical examples on compound stresses. Let us start with the first problem. At a point in a strained material, the normal stresses 80 MPa and 60 MPa, both tensile, are acting on two mutually perpendicular planes. If one of the principal stress is limited to 110 MPa tensile, find the other principal stress. Also find the shear stress acting on the given planes and the maximum shear stress. So the normal stress 80 MPa and 60 MPa are acting on two mutually perpendicular planes and they are tensile. Let us take 80 MPa in x direction and 60 MPa in y direction. You may take 60 in x direction and 80 in y direction. That will not change the required result in this particular example, but the stresses orientation will change. It is as if the element is rotated by 90 degree. Now if one of the principal stress is limited to 110 MPa tensile, okay, you have to find out the other principal stress, shear stress associated with the planes and maximum shear stress. So you know sigma x is 80 MPa tensile, so plus sigma y is 60 MPa and it's also tensile, and one of the principal stress is also given as 110 MPa tensile. Now you have equation sigma 1 as sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 square plus tau xy square. So this is expression for principal stress. So plus or minus sigma 1 and sigma 2 are plus or minus. So I will take the plus sign. One of the principal stress is limited to 110 MPa tensile. Since principal stress value given is more than these normal stresses, 80 is the megapascal is the maximum normal stress and it is more than 80, so this is a major principal stress, so I have taken plus. If it's less than 60, you can take minus. So 110 is equal to 80 plus 60 by 2 plus root of 80 minus 60 by 2 plus tau xy square. This is unknown, so you get 110 is equal to, this is 140 by 2 or 70 plus root of 80 minus 60 is 20 by 2 is 10 square 100 plus tau xy square, or 110 minus 70 you get 40 is equal to root of 100 plus tau xy square. Squaring on either side you get 40 square is equal to 100 plus tau xy square, or tau xy you can solve it as 38.73 MPa. So much is the shear stress associated with the planes. So if a shear stress is 38.73 MPa, you will get one of the principal stress as 110 MPa. So you got the shear stress associated with the planes. Now to find out the other principal stress, you may use this equation with the minus sign, or we have known property like this: summation of the normal stresses on any two mutually perpendicular planes is equal to a constant, and it's equal to sigma x plus sigma y. And since principal stresses are normal stresses on mutually perpendicular planes, you can even apply it for principal stresses, so that sigma 1 plus sigma 2 is equal to sigma x plus sigma y. From this you can get sigma 2 as sigma x plus sigma y minus sigma 1. So 80 plus 60 minus 110. You get sigma 2 as 30 MPa. So minor principal stress is 30 MPa and major principal stress was given 110 MPa. So you got the principal stresses, and now let us find out the maximum shear stress. Maximum shear stress you can use sigma 1 minus sigma 2 by 2. Sigma 1 is major principal stress is 110 and minor is 30, so sigma 1 and sigma 2 divided by 2, that is 80 by 2 or 40 MPa. So maximum shear stress is equal 40 MPa. So you got the shear stress associated with the planes, minor principal stress, and maximum shear stress. Now let us work out another example. A machine part is subjected to stresses as shown in figure. A circle of diameter 200 mm on the member is converted to an ellipse after the application of stresses. Determine the major and minor axes of the ellipse and their orientations. Take E is equal to 2 into 10 raised to 5 megapascal and Poisson's ratio as 0.3. So an element on machine part is subjected to stresses as shown in figure. So in the x direction you have 150 megapascal, in y direction you have 100 megapascal compressive stress and shear stress acting 75 megapascal. So in x direction you have tensile stress, so plus, in y direction you have compressive stress minus 100 megapascal, and shear stress on the right face it's upward, so plus 75 megapascal. Now there is a circle drawn on the member of diameter 200 mm. Now this circle will deform as a result of the stresses. When the stresses are applied, one direction you will have maximum principal stress and another perpendicular direction you will have minimum principal stress, or it may be a compressive stress, maximum compressive stress. As a result of that, the circle will deform into an ellipse and you have to find out the major axis. So major axis will be greater than 200 and minor axis will be less than 200. Since compressive stress is also associated with this, one of the stress will be tensile. So major principal stress is going to be tensile. It will be greater than 150, and other principal stress is going to be compressive and it is going to be greater than 100 megapascal. So one direction you will have tensile stress and another direction you will have compressive stress. As a result of tensile stress, the element will deform and the diameter of this circle drawn will increase and it will be more than 200 mm. Whereas a perpendicular direction you will have compressive stress and the diameter will decrease and it will be less than 200 mm. Now you have to find out what is the increase and what is the decrease in diameter in these directions. So finally you should find out the major axis and minor axis of this ellipse. Now let us find out the principal stresses and its directions. So principal planes, tan 2 theta p is 2 tau xy divided by sigma x minus sigma y, and tau xy is plus 75 and sigma x is 150 and sigma y is minus 100. You will get tan 2 theta p as 0.6. So from this 2 theta p you can solve as 30.96, or theta p1 is 15.48 degree, and theta p2 you can add 90 degree to this, which will give 105.48. So you got the orientation of principal planes. One of the plane is 15.48 degree and another plane is perpendicular to that, that is 105.48 degree from the vertical. So both these angles are measured from the vertical. One of the plane inclined 15.48 degree, positive means counterclockwise direction, and another plane perpendicular to that. Now after getting the principal plane, you have to find out the principal stresses. But in this case, instead of going for direct formula to find out the principal stresses, we will substitute the angle in the normal stress equation and find out the principal stresses. We will substitute the principal planes in this angle and then find out the normal stresses on the principal planes. Since we have to identify the stress associated with this plane, okay, so this particular plane 15.48 degree, what is the stress associated, principal stress associated? So to identify that, we have to go for normal stress equation and substitute the principal plane angles. So we will find out the principal stresses. Sigma is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. So this expression for normal stress. Now let us substitute the sigma x, sigma y and one of the principal plane angle, that is 15.48 degree. This will give the principal stress associated with this 15.48 degree plane. So you get 170.774 megapascal tensile stress. So on that plane, this is the principal stress and it is a major principal stress. Now you can apply this equation, sum of the principal stress or sum of the normal stress on any two mutually perpendicular planes. Here I have taken principal stresses is equal to sigma x plus sigma y, and now we have sigma 1 is 170.774 plus other principal stress sigma 2 is equal to sigma x is 150 and sigma y is minus 100. So you get this 50 minus 170.774, you get minus 120.774. So this is compressive. So major principal stress is tensile and it is 170.774 and minor one is minus 120.774, and that tensile stress will act in this direction on this 15.48 plane. So the tensile stress will act perpendicular to that, the compressive stress will act. Let us show it on a diagram. Now this is a 15.48 degree plane, and on this plane normal to that stress will act. So this is the direction in which this is a plane, a first principal plane. On that plane, normal to that will have that major principal stress 170.774. Now perpendicular to that, perpendicular to this plane, you will have compressive stress. So perpendicular to this plane, you will have compressive stress acting like this. So this is a principal plane. When you have a principal plane, normal to that stresses will act. So this direction you can measure from the horizontal as 15.48. The plane is inclined 15.48 from the vertical, but its normal is inclined from the horizontal by 15.48. So the direction of principal stress or major axis from the x-axis, it is 15.48, and minor axis direction will be 105.48. So that is a principal plane angle only. Same angle if you measure from the x-axis, you will get the direction of principal stresses. So you got the direction of major axis of the ellipse and minor axis of the ellipse. So major axis will be in this direction because as a result of this pull, the diameter will increase, and also this compressive stress is increasing the diameter in the perpendicular direction. And now in this direction the diameter will decrease because of the compressive stress and also because of this tensile stress. This tensile also is decreasing the diameter, lateral strain is induced here. So you have to find out the major axis and minor axis of the ellipse. You can find out the strain in this direction. Strain in this direction, in the direction of major principal stress. So that is this stress divided by Young's modulus. That will give the direct strain, and lateral strain due to this also you should find out. That will be minus nu sigma 2 by E. So you can use that expression to find out the strain in this direction and strain in minor axis direction. So strain in major axis direction and strain in minor axis direction you should find out. So strain along the major axis will be sigma 1 by E minus nu sigma 2 by E. That is sigma 1 by E in this direction, sigma 1 by E minus nu sigma 2 by E. So that will be the strain along the major axis. So it is 170.774 divided by Young's modulus is given 2 into 10 raised to 5, and Poisson's ratio is also given and sigma 2 is minus. So substitute that minus value, compressive stress, get Young's modulus here. So you get the strain along the major axis as 0.001-035. So this is strain along the major axis. Now strain multiplied by the length, that is a diameter is 200 mm. So in this direction you have a strain of so much. Strain means the change in length per unit length multiplied by the original diameter, you will give the increase in diameter. Since it is a positive strain, you will get an increase of so much. So diameter will increase by so much. So this you can add to 200. So major axis of the ellipse is 200 plus 0.207 or 200.207 mm. So that will be the major axis. And now you need to find out the minor axis. To find out the minor axis, you should find out the strain along this axis. So that is sigma 2 by E minus mu sigma 1 by E. So use the equation. Strain along the minor axis is sigma 2 by E minus mu sigma 1 by E. So it is minus sigma 2 is minus 120.774 divided by Young's modulus is 2 into 10 raised to 5 minus 0.3 into sigma 1 is 170.774 divided by 2 into 10 raised to 5. You will get the strain and you get a negative strain. So decrease in diameter you can find out. So the strain multiplied by the initial diameter. So that will give as minus 0.179 mm. So after getting the decrease in diameter, you can add to the initial diameter, that is 200 mm. So 200 minus 0.179, that is adding this, you will get the minor axis of the ellipse 199.821. So you got the major axis and minor axis of the ellipse. So major axis will increase and the diameter will be more than 200, minor axis will decrease and the minor axis will be less than 200. Let us work out another example. At a certain point in a material under stress, the intensity of the resultant stress on a vertical plane is 10 Newton per mm square. Inclined at 30 degree to the normal to that plane, and the stress on a horizontal plane has a normal tensile component of intensity 6 Newton per mm square as shown in figure. Find the principal stresses and the location of the planes on which they act. So the intensity of resultant stress on a vertical plane you have 10 Newton per mm square, but it is inclined 30 degree. So this is a resultant stress and on this plane, vertical plane, and that makes an angle 30 degree from the horizontal. So this will have a component, normal component and tangential component. The normal component is normal stress, tangential component will give the shear stress. And also given that on a horizontal plane, the normal tensile component is 6 Newton per mm square. On the horizontal plane, the normal tensile component is 6 Newton per mm square. So this is a component of the stress acting on this plane. So other horizontal component is not given, but horizontal component has to be equal to this shear component here. So y component of this stress is going to be the shear stress acting on this vertical plane, and even horizontal plane you should have the same value of shear stress. So this component is 10 cos 30 and that will give the normal stress, and 10 sin 30 will give the shear stress. 10 sin 30 is 5 megapascal. 5 megapascal will be shear stress. So here also you should have same amount of shear stress, 5 megapascal or 5 Newton per mm square. So you have to resolve this and get the normal stress and shear stress, and the same shear stress will be acting here. And the part of the element is shown. The x component is 10 cos 30, which is 8.66 Newton per mm square, and in sigma y is 6 Newton per mm square. And tau xy, the y component of this 10 sin 30, which is 5 Newton per mm square. So you got tau xy also. It is y component is going to be upward. So that is 5 Newton per mm square. As per complementary shear stress theorem, even the horizontal plane should be associated with the same amount of shear stress, 5 Newton per mm square. So after getting the stresses, you can find out the principal planes. Tan 2 theta p is equal to 2 tau xy divided by sigma x minus sigma y. Tau xy is plus 5 because it is upward on the right face. So 5, sigma x is 8.66, sigma y is plus 6. Substitute that, you get the tan 2 theta p as 3.759. So you can solve for 2 theta p 75.1 degree. Dividing this by 2, you will get theta p1 as 37.55 degree. And now you can find out the second principal plane by adding 90 degree to that, that is 127.55 degree. You can find out the principal stresses using the equation sigma 1 and sigma 2 as sigma x plus sigma y by 2 plus or minus root of sigma x minus sigma y by 2 square plus tau xy square. Substitute the values of sigma x, sigma y and tau xy. You get the principal stresses as 12.504 Newton per mm square and 2.156 Newton per mm square. So plus value corresponding to this, minus value gives a minor principal stress. These are the principal stresses associated with the component. That's all for today. Thank you for watching.